All right, we are on the air now, and I thought I would start class today just with a quick Q&A about the exam, since it's in 2 weeks, but I'm going to be away next week. In case there are any questions, I can field them this week. There's a bit of information about it in the syllabus. I think that that it's an open book exam, and I posted a few things about it in class today, or on the Blackboard announce. But are there any questions about it? Just briefly, it's going to cover all of the sessions up until next week, so 1 through 4. It'll cover anything that has been in the lectures, the labs, or the assignments. You will be able to use a computer, either one of the school's computers or your own, plus a tablet, any other kind of device that you want to use. It's an open book exam. Basically, you can bring anything that you want into the exam, except a friend. You can't communicate with the outside world, and you can't use the internet to be looking up new stuff during the exam. Anything that you have gotten, like textbooks, notes, anything like that, in advance, you're welcome to use it as part of your preparation. The exam will be administered through Blackboard. It'll be a combination of multiple choice, some fill in the answers, and some essay type right in the answers. It'll go the full period, so 5 p.m. till 7:50. It'll be my goal to make it so that you're not under too much time pressure. You shouldn't have too much trouble finishing it in the 2 hours 50 minutes that you have in class. So I don't like to put too much time pressure on exams. Are there any questions about it? Oh, and also I'll mention that I've posted some example questions from previous exams along with solutions for them. Yes.
So the example question link is not working.
Oh, the link is not working. Okay, I'm sorry. I'll figure that out. But that's great to know that someone has looked already. Any other questions? Okay, if you do come up with any questions between now and later, feel free to post them on the discussion board in Blackboard, or email them to me. Although if you email them to me, I might respond on the discussion board anyways, just so that everyone can answer. I will admit I'm not in the habit of necessarily checking the discussion board all the time. So if you post a question there, maybe just also fire me an email to let me know there's a question there. So I'm gonna start my screen share here so we can begin our lecture. Because of some authentication problems I'm having here, we're actually broadcasting from my laptop and just watch screen. Remember to switch on both things here. Okay. And by the way, how did you all find the first assignment? Okay. Okay. Yeah.
I was going to mention, I still have a lot of questions on the president's chart and on those chart A, B, and C. I'm going to go over that and get it from the lab. And then I'm never going to use those charts again for the rest of my life. There are so many questions.
The president's chart, okay. Okay. There are no president's charts on the exam, I can tell you that, so. But it'll do you good like spinach, maybe. All right, we're finally gonna move beyond the stuff that almost everyone has heard of before onto some stuff that's probably new for a lot of you. And I'm going to talk about screening tests and as an introduction to some ideas about probability and Bayes' theorem. So some pretty interesting probability stuff with very useful applications and stuff that is probably new for many of you. And this time I'm going to start with an example. So let's say, and this is going to be a little quiz for you, we have a screening test that is correctly positive for 100% of cancer patients. So if you have cancer and you take this test, it will always say that you have cancer. Now, the prevalence of this type of cancer, let's say, is 5 per 1,000 people per year. Then if this test is applied to that general population where the prevalence is 5 in 1,000, what's the probability that an individual testing positive has cancer? So if you're part of this population and you go have the test and you get a positive test, how worried should you be? And this has come up a lot. This is, I'm kind of intentional, this is based a little bit on some controversies around screening tests in public health. So let's hear, what's that? How worried should you be? What if you receive a positive result from this test based only on the information I've put on this slide? What's that?
Can you repeat the question?
Okay, so this is a hypothetical screening test. It's not a real one. The only things that are known about it are on this slide. That's it, nothing else. All we know is we know the prevalence of cancer, and we know that the screening test is correctly positive for 100% of cancer patients. Or in other words, if you have cancer, it will give you a positive test. Yes?
Completely worried.
This test
Complete.
will contain a lot of false positives. Yeah.
False positives. Yeah.
Definitely.
This is a good point. So the point is that this test will probably have many false positives. What were you going to say? Opposite of that. I heard a couple I'd be very worried. Yeah? We should consider the sensitivity of the test. Well, the sensitivity of the test is here on the screen. The sensitivity is 100%. You know the sensitivity.
Meaning that if somebody tested positive and it's 100% of the time,
well, what I've said here is that if you have cancer, it's right 100% of the time. But there was a very good point at the back of the room that I haven't said anything about how accurate it is for people who do not have cancer. I haven't said anything about that. So as a result, we have no idea what the probability is, and I can't tell you how worried you should be. Keep in mind that in 1,000 people in the general population, this test is being applied to 9,995 healthy people and only 5 people with cancer. So all I told you is it's going to be right for those 5 people. I didn't tell you what it's going to do for those other 9,995 people. And that matters too, right? Because of false positives. So, and this is a cause of controversy and consternation and a lot of potentially worry and unnecessary treatment around not only cancer but other things, that tests that are highly sensitive can also have false positives. In fact, I told you so little here that the test could have just been as simple as a sheet of paper that says, yes, you have cancer, that's given to everyone who takes the test. Right? And that would be correct. That would meet these requirements, or what I said here, that it's correctly positive for 100% of cancer patients. So what I want you to take from this example is that you have to consider not only this true positive rate, but you have to also consider the false positive rate. There's also a false negative rate and a true negative rate. We'll also talk about this in terms of sensitivity, specificity, positive predictive value, negative predictive value. Because ideally, we would have tests that were just 100% accurate, but that's not reality. We almost never have tests that are 100% accurate. And with tests that make mistakes, there is generally a trade-off between false positives and false negatives, and you have to make a decision about how to make that trade-off. And this idea of there being a trade-off between false positives and false negatives is not limited to diagnostic tests. It's limited to the whole world and anything that you might think of where there's uncertainty involved in a decision. In fact, I have become so indoctrinated with this idea of the sensitivity specificity trade-off that I think about it in all contexts. You'd be hard-pressed to find a context in which I can't talk about sensitivity and specificity. Just to give an example, when you hear discussion about, you know, when there are terrorist attacks and like why did security services not anticipate this advance, I think of that in terms of the sensitivity specificity trade-off. If you wanted to be 100% about terrorist attacks and never miss one, you would have to have terrible specificity and probably just incarcerate everyone. So, or I don't know, any other examples where there are uncertainty? I mean, paroles is another one where it comes up in the news that I think about it, like, you know, concern about offenders released on parole who commit another crime. If you want to be 100%, you know, never have a false positive where someone is released and reoffends. To go to the other extreme means that you never release anyone. So, and anytime you go somewhere between those extremes, there will be some false positives and some false negatives. So that's the main idea behind this, this story. And the other one is that the performance of a test depends both on intrinsic values of the test, how it performs on cases and how it performs on controls, or how it performs on diseased people versus healthy people, but also on the population that it is applied to, because the population that it is applied to affects how many healthy people and how many diseased people it is applied to. So this is kind of intuitive. You have the intrinsic values of the test, or how does it do when applied to positive cases, and how does it do when applied to negative cases. But the overall performance depends on how many positive and how many negative cases you apply it to. And when I talk about this in the context of diagnostic tests, we'll talk about a gold standard, which is some highly accurate but probably expensive test that is not practical to do as a screening test on a population. Any questions so far? Yeah.
When someone says that a questionnaire or something is validated, is that where this might come into play?
When
it's
people
been used enough times that they can accurately predict its value?
when a questionnaire being validated, I feel like is getting it. It could be getting at this, it depends on the purpose of the questionnaire. I'm specifically talking about prediction here. So if you're talking about a questionnaire that is supposed to predict whether someone is at risk for something, and then you know later whether or not that outcome occurred, then validation would be about testing its sensitivity and specificity. But I think, you know, in other contexts, questionnaires, the purpose of them is just descriptive of the person, and the validation is more that you find that these questions are representative and complete and things like that.
I've seen it, that's kind of where I come from, is in predictive
It's a predictive questionnaire.
Diagnostic.
Right. Yeah, it's a good point. And yes, if you have a questionnaire that is supposed to predict, say, whether someone has clinical depression, and then you, on the test subjects, actually bring them for a clinical exam as the gold standard, then after you have assessed the accuracy, its sensitivity and specificity, then you could call it a validated questionnaire. Good question. Second example, and one with some slightly more realistic numbers in it, so we can do a few calculations. I'm going to talk about a screening test for chlamydia. This is one screening test that's going to be applied to two different populations. The first is the population of patients in a walk-in sexually transmitted disease clinic where there is a high prevalence of chlamydia, 30%. And then the second one is in a private practice where there is a much lower prevalence of true chlamydia cases, only 3%. So in each of these cases, there are 1,000 people. This is a manufactured example. And so out of these 1,000, because in the STD clinic where the prevalence is 30%, we're going to have 300 positives and 700 negatives. And this is the gold standard truth here. So not a realistic situation. This is where we know the truth for everyone, just because this is an example. So we've got 700 negatives, 300 positives. Now, for this PCR test, among the positives, we've got 294 that are called positive and only 6 that are called negative. And among the negatives, we've got most of them called negative, 679, and 21 are false positives. So from here, I can calculate the so-called positive predictive value. That is the probability that if the test, it's what we were talking about in the first example. So it's the probability that if the test gives you a positive result, that it's correct, that you do in fact have the condition that it is testing for. So looking at only the positive cases, we have 294 over 294 plus 21, it works out to 0.93. So this test has a 93% positive predictive value. In other words, in this clinic, if you walk in and get the test and you are typical of the population of patients in this clinic, you have a 93% chance of actually having chlamydia. And the negative predictive value, that is, if the test gives you a negative result, the probability that that you actually do not have the condition it is testing for is excellent. So here are all the negative tests. Only 6 are incorrect, 679 are correct. The negative predictive value is 679 over 685, which is about 99%. Now let's apply this exact same test to the private practice with a prevalence of 3%. And in this case, so among the positives, the accuracy is the same, and among the negatives, the accuracy is the same. So you see it's about, I don't know, what is this? About 50 to 1, it's about 50 to 1 here too. The corrects to incorrects among the positives, and it's the same performance among the negatives. But in this case, the positive predictive value, that is the performance among the positive test results, is only 50%. So among the people who got a positive test result, 29 of them did in fact have chlamydia and 29 did not. So the performance is far inferior in this other clinic. Yes?
And B is what represents that there?
B is what represent, B would be the false positives,
Yes.
Right. Right, so the true positives and the false positives are happening with the same frequency. So this is a really important thing to remember about diagnostic tests, that first of all, these very important properties, these positive predictive value and negative predictive value are the things that actually matter to the patient. The patient doesn't necessarily care about intrinsic properties of the test, how it performs on positive cases and negative controls. They care about them and what it means for them to receive a positive or negative result. And that very important thing depends on the prevalence of the condition in the population from which they're coming. It's a little bit counterintuitive, and I think it's even counterintuitive for a lot of public health professionals, and this is why some very promising diagnostic tests have been applied to the general population for low prevalence conditions and resulted in a lot of false positives. And this is, yes?
Can you please elaborate why the predictive value, the positive predictive value is different in two settings?
Yeah, why is the positive predictive value different in these two settings? The answer is because you're applying it to a lower prevalence population. As you take the same test and apply it to rarer and rarer disease, the positive predictive value will always decrease because you are giving it to a lot more negative cases. So you know, if your test has the same specificity, say it has, you know, it makes a mistake in 1% of negative cases. If you apply it to 100 negative cases, then it makes one mistake. If you apply it to 1,000,000 negative cases, then it makes 10,000 mistakes. So it makes a big difference whether your population is, there will be 100 cases out of every 200 people, or whether there are 100 cases out of every 1,000,000, because there will be way more false positives when you have 1,000,000 negative cases. So that's why the PPV has gone down here in the private practice. This was a nice little article here about uses and abuses of PPV and NPV and sensitivity and specificity. And that's where I actually got this example from, and they talk about it in some more detail. So let's get on to some probability here. Starting with some definitions. An event is some measurable definite outcome, such as whether an individual has a chlamydia infection, yes or no. Whether an individual survives past 70 years of age, yes or no. Whether an infant survives through their first year of life, yes or no. So these are measurable things that have a yes or no answer. And that's what I'm going to be talking about in the context of diagnostic tests. There has to be a definite yes or no answer. And probability is the rate of that event for some very large number of variations. So the probability of having chlamydia in an entire population as a percent, the probability of surviving past 70 years, or of an infant surviving in their first year, something that is averaged over many thousands or millions of people would be the probability. I've mentioned these intrinsic properties of a test. Importantly, sensitivity, that's the probability of a positive test for individuals with the disease. So a highly sensitive test is like the one I talked about on the first slide, where if someone has the disease, they get a positive test. That's sensitivity. So a highly sensitive test doesn't miss any positive cases. Whereas specificity is the probability of a negative test for individuals without the disease. So it's the performance on the negative controls. And both of these are just accuracies for positive cases and negative controls. So the sensitivity is the percent accuracy on the positive cases, those with the disease, and specificity is the accuracy on those without the disease. So if you can remember it like this, then these two things are very simple. They're just the accuracy on people with and without the disease, although it's easy to get them mixed up in your head sometimes. For me too. Yes?
In the previous example, we can say that the 0.99 is the specificity of the test and the chlamydia infection.
No, this is positive and negative predictive value. So these are not intrinsic properties of the test. I will write down definitions of PPV and NPV, but in terms of conditional probability that we'll be talking about a lot, positive predictive value is the probability of having the disease given a positive result. Sensitivity is the probability of a positive result given that you have the disease. So the conditionalness is reversed for PPV and NPV compared to sensitivity specificity. Here's an example for sensitivity and specificity. Now that I've given you the definition. Type 2 diabetes mellitus is highly prevalent in older and especially the obese US population. And a gold standard diagnosis, it requires this oral glucose tolerance tests where subjects drink this glucose solution, and then they have to fast, and blood is drawn at intervals for measurement of glucose. So they get this injection during a fast, and then they have repeated blood tests for a period after. So you can imagine this takes time, and it's invasive. They need to be in a clinic probably the whole day while this is being done. And the screening test is this fasting plasma glucose, which is done so they just come into the clinic not having eaten and have their glucose measure read. There's no waiting all day to get the result. It's just a single measurement after they haven't eaten for a period of time. So it's easier, faster, more convenient, less expensive, but also has inaccuracies. So in this example, thank you to someone at Johns Hopkins who made their lecture public with these nice diagrams that I have borrowed. So let's look at a hypothetical 40 people here that have, where there are 20 diabetics and 20 non-diabetics. And in this imperfect fasting single time point blood glucose test, their glucose levels might look something like this, where so it's a continuous measurement, and I've just put a qualitative axis on here from low to high. And among the diabetics, it looks somewhat higher than among the non-diabetics, but there's a lot of overlap because individuals naturally have a fair bit of variation in their fasting blood glucose, whether or not they have diabetes, which is why for a more accurate test you need a time series for that individual. So to have a test that just gives you a yes/no answer, you're going to have to set a threshold here. And setting here a low threshold, so any blood glucose above this level is going to get called a positive by the test because they're not processing the glucose properly and it has built up in their blood. So in this first example, I'm setting a low threshold. And so if you're below that, you're okay. If you're above that, then we're going to diagnose you with type 2 diabetes, at least based on the screening test. So let's fill out this 2x2 table here for these 40 people. Among the diabetics, so these are the true positive cases, we've got 17 positives and 3 negatives. And among the non-diabetics, 14 positives and 6 negatives. So from that, I can calculate the sensitivity and specificity of the test in these 20 people. Sensitivity is the accuracy on the positive cases, which is 17 out of 20, 85%. And the specificity is the accuracy on the non-cases. So it's only correct here on 6 out of 20 for a specificity of 30%. And you can see that over here that it's doing pretty well on the diabetics. 17 out of 20 of them have been called diabetic, but it's doing terribly on the non-diabetics. It's calling most of these non-diabetics as having diabetes. And my purpose here is to show this sensitivity specificity trade-off. So this trade-off is something that occurs in a given population without changing the prevalence. So I'm changing these intrinsic properties of the test as applied to a single population. I'm trying to separate out in this class things that are intrinsic to the test. Sensitivity, specificity, these are how the test performs on cases and controls, versus properties of the test when applied to a certain population. Sensitivity and specificity are intrinsic to the test, so they don't depend on the population. They only depend separately on the performance of the test on cases and on controls, and there is a trade-off. So in any population, assuming that the test is not 100% accurate, if you want better specificity, you need to trade off and lose some sensitivity, and vice versa. So by raising the bar here on what I will call positive test results, I'm making a different choice on that sensitivity specificity trade-off. And what I'm doing is I'm going to accept a much worse performance here on the diabetics. So now only 5 out of 20 get correctly diagnosed with diabetes, and the sensitivity is now down to 20%. But in exchange, I've gotten much better specificity. Only 2 non-diabetics out of 20 have been given a positive test result. So the specificity has gone up to 90%. So this is a fundamental, I don't know, law of the world here, that in anything where you have imperfect predictions and you have sensitivity and specificity, there's going to be a trade-off between them. And if you want better sensitivity, you'll lose specificity, and vice versa. Of course, in a typical population, there's no line separating the groups, and the subjects are mixed, because when they come in for the diagnostic test, we don't know whether they have diabetes or not. So it looks more something like this. And all we know is their glucose measure that we take and where the threshold has been set for this test. And it's not until it's during a development of the test in a clinical trial where we have a gold standard being applied to everyone, both positives and negatives, will we actually know the sensitivity and specificity of the test. So that high threshold that we set, all we will know is that it's giving us 7 diagnoses and 33 diagnoses. And the low cut point, by contrast, predicts that a lot more people have diabetes. So to conclude on our discussion of sensitivity and specificity, different cut points. This is for a test that results some continuous prediction, but we want a yes/no answer. Different cut points between where you diagnose a positive and a negative yield different sensitivities and specificities, and they control that trade-off between sensitivity and specificity. And a higher cut point gives you better specificity but worse sensitivity, whereas a low cut point gives you good sensitivity, you won't miss too many people, but at the expense of specificity or a lot of false positives. So that first example that we talked about, the cancer screening test that correctly identifies 100% of cancer patients, would have looked something like, most likely raising this high sensitivity right up to the top. So it's just giving a positive result for everyone in the population in order to get 100% sensitivity. Unless it's a perfect test, which isn't likely. So moving on to positive predictive value and negative predictive value. Recall that I said sensitivity and specificity, these are intrinsic properties of the test itself. So they have to do with the laboratory procedures and with where the cut point is set, but it doesn't depend on populations or prevalence. It's an intrinsic property of the test. Whereas positive predictive value and negative predictive value are properties of the test when applied to a population with a given prevalence. And these are the things that matter the most to patients and physicians. So the positive predictive value, that's the probability that someone receiving a positive test indeed has the disease, and negative predictive value is the probability that someone receiving a negative test really does not have the disease. Both different and important aspects of the performance of a diagnostic test. So back to this diabetes example, with the high threshold, our positive predictive value was 5 out of 7, and negative predictive value 18 out of 33. Just to show that the if you write out a 2x2 table like this, the sensitivity and specificity are calculated along one direction, and the PPV and NPV are calculated along the other direction. And obviously, both of them are going to be affected by where you set this cut point. As I mentioned, PPV has caused great debate in public health, because when you apply screening tests to low prevalence diseases like prostate cancer, breast cancer, and certain mental health conditions, you will have a lot of false positives, and those false positives indeed have a public health impact as well. So, but it is a cause of debate because these are imperfect tests, and so anywhere that you set a threshold, there are going to be mistakes, and those mistakes will have costs in terms of people's health. And in cases of very serious diseases like cancer, there is certainly a desire to not miss any cases, to have a very high negative predictive value, so that if anyone has cancer, you catch it. But that, of course, comes at this trade-off of a significant number of false positives. So it becomes a challenge of how do you weigh the costs of each of those kinds of errors. In cancer tests, the best available kind of way to weigh this trade-off is through a long-term clinical trial, where you have where you randomize people to one group where they receive the test and another group where they do not, and then you just look at their overall survival over a long period of time. But that, of course, takes a very long time to complete. A trial like that can take 15 or 20 years to complete, so that you can follow, especially for diseases like prostate cancer and breast cancer, where there tends to be a fairly long survival of a lot of the patients, and there also tend to be a lot of people who do not have an aggressive form of the disease, so can survive a long time even without treatment. But short of that, it's very hard to define trade-offs between missing a diagnosis of cancer or having unnecessary treatment and other injury from the false positive. So I've given you lots of examples so that I can now just move into some probability stuff, without having you worry that there's no reason for learning this stuff. Let's introduce a bit of probability notation that's going to let us write out these concepts in a probabilistic formulation. I'm going to refer to different events as A and B here. These could be something like two different outcomes, like cancer and heart disease. These could be, they could be things that are exclusionary events, like having cancer or not having cancer, and we'll be able to express things like this through the notation. So the U stands for union, A or B. So if in the cancer heart disease case, union would be having either cancer or heart disease. Intersection referring to and, having both. The C is a complement, so not A. So that would be like not having cancer, not having heart disease, such that the probability of an event plus the probability of its complement always equals 1. The first law of probabilities, that the sum of the probabilities of all mutually exclusive exhaustive events always adds up to 1. And one more very important piece of terminology here is this little bar, which we use for conditional probability. And this you can read as the probability of A conditionally on B being true. So here I'm talking about the probability of an event A if B is true. That's a conditional probability because it's conditional on B. You can visualize these as Venn diagrams, drawing A and B as circles. Then the overlap between them is A intersected with B, or with 3 events. The overlap between A and B, you can see up at the top here. Where's my mouse pointer? There's the intersection between A and B, and the area common to all 3 circles is A intersect with B intersect with C. These are Venn diagrams. All right, a few questions for you. Practice questions. I've drawn some Venn diagrams here. How would you write the probability shown in this top left Venn diagram? Yep. A intersection B. Let's see, this down here on the bottom right would be A intersection with B. I don't have my... Yeah, it's just the probability of B, because the green here is the probability of event B. How about this top right one? Yes. A union B. Very good. This third one is probability of A. There are different ways you could write this out, but the simplest way is probability of A.
No, I mean the second one, I'm not sure, but you said that A union B.
Mm-hmm.
We already have the intersection.
Yeah.
Should subtract it.
Well, A union B minus the intersection would exclude this bit in the middle. We don't have a case like that here. Yep. Number 2. Number 6 is the intersection. That's A and B. That's where it's enclosed in both A and B. Sure, let's talk about cancer and heart disease, where A is having cancer, B is having heart disease. This includes both events. So This is your probability of having either cancer or heart disease, or having both. That's the union. Whereas the intersection would be only having both cancer and heart disease. All of this area that's one or the other doesn't count. Here's a tricky one. What about it? Number 4. Probability of A minus the intersection. Yeah, that's one way to do it. Was there another answer? Yeah, A intersect with B complement would be another way to write this. So B complement means anything not B, and that intersected with A. So B complemented would be the entire box here outside of B, but only this part of it is also A. Sorry? So this number 4, I don't know why I can't, see if I can't quite write on the slide, but number 4, so first of all, the probability of B would be everything inside the circle B. Probability of B complement is everything not inside the circle B. So it would be this entire rectangular region, anything that is not inside circle B is B complement. So this green bit is both inside A and not inside B. Or another way to say that is it's A and B complement, or A intersect with B complement. You probably, I mean, you're not going to need to do too many exercises like this, but this is just to start getting used to thinking a bit about probability. It is important that you remember some things like you know, the difference between an event and its complement, and things like that. That will be useful. Yes? The middle left one, so number 3, yep. Sorry? So this one would be probability of A intersected with, or sorry, this is just probability of A, period. It's everything within A. It doesn't matter whether it's in B or not.
I'm sorry, I want to go back to this number 2 again, because we learned before that if we said that probability of A plus probability of B, so we are making double of the intersect. That's
right.
Why we have to subtract from the intersect.
Yeah, so we're not yet actually doing this adding of probabilities of 2 events. We will do that, but yes, when you want the probability of A or B, you have to be careful not to double count the intersection of them.
So it's here, it's just in.
So for example, number 2, this probability of A union B is not equal to the probability of A plus the probability of B, because part of that is shared by both of them. So if you were to just take the area of A plus the area of B, you would have to subtract off the area that's in common to both of them for getting the probability of A plus probability of B. Yep.
When you word it like that, the area,
yep.
would be like the probability of A with the probability of B, taking out that middle area, that they're happening at the same time. Like if we're adding them.
Yeah, so the question, I guess, was how to calculate the probability of A union B, or A or B. And in order to do that, if they're mutually exclusive events, like a coin flip, then you just add the 2. If they're not mutually exclusive, like cancer and heart disease, you have to add the 2, and then you have to subtract the probability of both.
So meaning that they're not happening at the same time.
They can happen at the same time. And the point is that if you want the probability of having cancer or heart disease, let's say in some very sick population, probability of cancer is 50% and probability of heart disease is 50%, the probability of having one or the other isn't 100% because you have some people who have both. You have to subtract the probability of having both then. Called mutually exclusive if there's no overlap between them, like having a condition and not having the condition. And in this case, this is what we've just been talking about, but just writing it down, the probability of event A having chlamydia or event B not having chlamydia is just equal to the sum of those two probabilities because they're mutually exclusive. And if those options are exhaustive, then that probability adds up to 1. So there are no other possibilities than having chlamydia or not having chlamydia. The probability of chlamydia or not chlamydia is equal to 1. And that, in general, is a property of probability that your probability of all possible events must add up to 1. And because they are mutually exclusive, the probability of chlamydia and not chlamydia is equal to 0. Now, in cases that are non-exclusive, like chlamydia and heart disease, there is a non-zero intersection, the overlap in the Venn diagram, and then the probability of the union, so chlamydia or heart disease, is equal to the sum minus that area in the middle, exactly like you were saying. So probability of chlamydia on the left plus probability of heart disease, the circle on the right, minus the probability of having both, which is getting counted twice otherwise. And if they are independent events, then it is also just equal to the product of the two. So if the probability of chlamydia has nothing to do with the probability of having heart disease, then the probability of this intersection, the amount of area that is in the middle, is just equal to the product of those two independent events, or the probabilities of those two independent events. The key there being that they're independent. And if you just divide through that rule that I just gave, you get an equation that looks like this. So this comes from saying that this probability of A conditional on B is equal to the probability of A and B over the probability of B. And this is called Bayes' rule. It's just a basic rule of probability. In fact, some people have said that it's such a basic rule of probability, it just has to do with the commutativeness of intersections that it didn't even really deserve its own name. But it did get its own name, and it's used all the time in whole branches of probability, and it's used for calculating properties of a diagnostic test in the population. Just to show you how to derive it, so it's not a mystery. It comes from, you can just write out that the probability of A intersected with B is the same thing as the probability of B intersected with A. So probability of A and B, same as probability of B and A. The probability of having cancer and heart disease is the same as having the probability of heart disease and cancer. It's just the same thing. And then I write each of these these things out. So the probability of having cancer and heart disease, another way to say that would be that's the probability of having cancer conditional on having heart disease times the probability that you have heart disease. It's intuitive, or is it? Any questions about that? So I want to calculate the probability that someone has both cancer and heart disease. So, but I don't have that, but I do happen to have two other pieces of information. I know what the prevalence of cancer is in a population of people that have heart disease. That's the probability of having cancer given that you have heart disease. And I know the prevalence of heart disease. So if I know those two things, then I can calculate the probability of having both. Yeah, and then on the right, it's just the other way. It's like I know the probability of heart disease in the population of cancer patients, and I know the prevalence of cancer. So those are totally different numbers and different, one is the population of everyone with cancer, the other is the population of everyone with heart disease. But either way, I could arrive at the probability of having both. And so I write out this, this equation, which is just two conditional probabilities, and then just divide through by probability of B, and voila, we have Bayes' rule. That's all there is to it. It's the only equation I'm going to derive for you in this class, because you get a lot of bang for the buck. It's an important equation, and it's really easy to derive. In the language of Bayesian probability, probability of A given B is going to be called the posterior probability. This probability of A is the prior probability. Probability of B given A will be called the likelihood. And this denominator is sort of a normalizing factor. So in the example of calculating the probability of cancer given that you have heart disease, then the probability of having cancer in the general population would be your prior probability, then the probability of, wait, I got confused. What was I trying to calculate? I need to write this down. The probability, will stay in alphabetical order. So I want the probability of having cancer given that you have heart disease. The probability of cancer in the whole population, that's your prior probability. That's your estimate given no information. Then this probability of B given A, that's your probability of having heart disease given that you have cancer. Your likelihood, and then the denominator is the probability of having heart disease. So this is allowing us a different way of calculating this probability of having cancer. I could have chosen a better example here, which in terms of PPV, but you'll have plenty of chances to calculate this in terms of PPV. The important application that you're really learning this for is for taking the intrinsic properties of a diagnostic test, and from that, and the prevalence of a disease in the population, calculating its positive predictive value and negative predictive value. And Bayes' rule allows you to do that. So does probability of A given B, or A conditional on B, equal the probability of B conditionally on A? No. Very good. Very good. You've already picked this up. That only happens when the prior probabilities of both those things are the same. As an example, what's the probability you would retire given that you had as much money as Trump? Maybe high? Probably reasonably high. But what's the probability that you would have as much money as Trump given that you've retired? It's low. So they're just not the same things. We're running a little over, so I think I will skip this example from lecture 1. All I did was take this example that we used back then about the treatment and control in the clinical trial of a pain reliever and whether people reported mild, moderate, or severe pain, and just having you calculate a few things. Maybe we will just go ahead and calculate number 3, a conditional probability. What's the probability of a patient reporting mild pain conditional on them being in the treatment group? So to do that, we look just at the treatment group. It's conditional on them being in the treatment group. So you just look at this column and what's the probability of them reporting mild pain? It's 15 out of 50. 15 out of 50. Yeah. Whereas the probability of them being in the treatment group, given they are reporting mild pain, so the reverse conditional probability. So mild pain treatment group, it's 15 out of 20. Did I get that right? So one is in the columns, the other's in the rows. You can take a look at this one later, but it's just the same thing here. I'm going through, I'm using definitions of prevalence. Prevalence is just the probability of chlamydia in the screening test. Sensitivity is the probability of a positive test given that you have chlamydia, or the accuracy on positive cases. I'm just writing these things out in terms of the probability notation that you've just learned. But the key thing here is that now you have Bayes' rule. You can apply a given sensitivity specificity to a different population using this equation. So you can calculate the PPV and the NPV for any population. So in probably the most difficult kind of problem you might have to solve, you might be given the PPV and NPV in one population and asked what are the PPV and NPV in a different population with a different prevalence. And to do that, you'd have to calculate the sensitivity and specificity in the first population, and then use that to calculate PPV and NPV in the other population. I've given you a little spreadsheet in with the lecture notes to make those calculations easier. So, but you could do it by hand. The spreadsheet is handy. There are also Bayes rule calculators that you can get online to test things out as you're learning. So just to wrap up, probability of having a disease given the positive test is not the same thing of the probability of a positive test given that you have the disease. The first one is your PPV, the second one is your specificity. Here's just a wrap up of the intrinsic properties of the test, sensitivity and specificity, and the application of that test to the population, PPV and NPV. And a little notation cheat sheet for you, and that's the end. Any questions before we take a 5-minute break and go on to the lab? If you've thought of any questions about the exam since the last time, feel free to ask, or any questions about this or preceding materials. All right. Thank you, and see you in a few minutes.